we now okay, so assume now okay, you already pick a good tool, no matter what it is. Now you need to build the material layer by layer, and everything needs to base on your substrate because it's called epitaxy. Okay, so let's consider you're building material A on substrate B, but your material A has a different lattice constant with your substrate. But you need to fit that into the substrate. So the material will need to change its size to accommodate the seed. It's just like if you become a very fat people, but our seed is just this big. Then he need to squeeze his meat and so he will feel very uncomfortable. So we call this kind of material deformation. We evaluate it. We call it lattice-mismatched strength. Lattice-mismatched strength, and we can evaluate like that. The AF0 means its original size of the lattice constant, and the AF is its final size of the lattice constant. It's usually the same with the substrate because substrate is big, layer is thin. Okay, so if the substrate has a lattice constant smaller than your field, for example, okay, it's a good example. Silicon germanium is a mixture of silicon and germanium. But surely germanium is a larger atom, so its lattice constant is larger. But now you need to grow it on a silicon substrate, so the size will be twisted after growth. So its AF0 is larger than a substrate. So this will be a negative value. Because its original lattice constant is the one with the larger value. So the lattice constant is a negative value according to the definition. So while the lattice strength and probably we will times 100%. Yeah, for better looking number. So from H1 is less than, it's a negative number, that means the material is under compressive strength. Yeah, that is difficult because you're trying to combine different material into the same material device to build your laser or LED. In other way, if the material is originally smaller, but you want to grow it on a larger substrate, you need to expand the size to fit the substrate. So your AF is larger than its original value. So you get a positive lattice strength. Okay, then you got we call it tensile 张引力，然后这个是 compressive 是压引力。And that's the best scenario if these two materials has the same lattice constant. Then we call it strength-free or lattice-matched strength. And there's a good sample is aluminum arsenide on gallium arsenide. It's almost strength-free. Another good idea is Indian gallium arsenide with 53% Indian on aluminum arsenide. You can do VGASO to evaluate the lattice constant to measure the lattice constant of indium phosphide. It's also almost strength-free. So if what's the problem with strength? So strength could be benefit and then also detrimental. But in practical, it's usually detrimental. Because just like if you're really a very fat people to sit a very small scale, then he will feel very uncomfortable. Then he cannot see very low and then leave. It's the same reason for the field. If the AP field is under very strong strength, you cannot grow a very thick field. Because the strain energy will be stored in your device and eventually release that with a lot of defects. So then your crystal quality will be very poor, so you cannot make a good device. So there's some of the phenomena. For example, if you grow an InGaN on gate, InGaN has a compressive strength on gate, and if you have some dislocation within that, in blue LED, you will see a lot of pits. Okay. So some people say pit is good, some people say pit is not. But eventually, we decided to fix, so we want to avoid that. But it's possible. Sometimes we just cannot avoid that. You need to swallow that. There will be another issue. Another this is another the issue of the Indian arsenite, that's super compressive. So you cannot even get a good film. Before you get a good film, you just cannot stand it and become a quantum dust. Just it will aggregate with itself. It cannot form a film. Then this quantum dot is actually not a bad film, so it's not always bad. And so actually for the most of the quantum dot in semiconductor is triggered by the compressive field. Yeah. So there are so many different issues for different kind of strain material. This is another example. If you grow argon is the tensile field. If you grow it really thick, it will crack. It will cannot just binding with cell and then it's too tensile and the film just crack. Then after film crack, your device is dead. Yeah. So there are two ways to deal with this problem. One is that you do a very delicate straightening to understand how big you can grow your film. Then design your film with this limit. It's just growing, just like growing along a rope. Yeah, because it is a dangerous path, but you need to grow that. So that will be very highly delicate engineering job. But there's another route. Is that how can we just design with device with the same lattice constant? So then we don't need to be bounded by the material constant itself. Okay. So this is some common line. So the materials with the symmetry constant means those are material in the vertical line of the figure above. So there's a few common lattice-matched systems. The first is outgas on gas. The lattice constant of aluminum arsenide, is almost the same. Its lattice constant strength is only minus 0.12%. So materials between that the strength is all less than. It's slightly compressive of aluminum arsenide. Yes, but because you can grow very thick film with this number of strength, so we usually regard aluminum arsenide and gallium arsenide as a strength-free system. That means you can design the material along this line with different band gaps without great difficulties. Although there's a transition of band gap between direct band gap and indirect band gap. Yeah. So if you want trying to make a device with wavelengths ranging from around 1 micron to 700 nanometer, it's easily achievable without gas epitaxy on gallium arsenide substrate. However, that's just as I stated that if it's the 980 nanometer VSO, the film is high 980 VSO, basically you need to grow a 20% in gas, so it's actually compressive strength. But since we only need to grow that layer with 3 nanometer, so it's still acceptable. However, if you want a material with a shorter wavelength, you need to increase your Indian composition inside. While you're creating more Indian, the compressive strength is become larger and larger. You even cannot go a 3 nanometer film. Then you need to change your material system. So also because we let's face another for the gas and outgas material, the direct band gap material is from 900 nanometer to 650 nanometer. If you want to grow a device with a wavelength shorter than that, it's in direct band gap material. is out of the design space. So there's another design space is called ALINGAP on gallium arsenide. So aluminum aluminum phosphide, the band gap smaller than gallium arsenide. Indium phosphide have a lattice content larger than gallium arsenide. So if you do a simple bgas law, you will see it's around 53% aluminum indium phosphide is lattice matched to gallium arsenide, and it has a band gap. And the second, you can also see that for the gallium phosphide and the indium phosphide, after doing some calculation with bgas law, it is about 52% of gallium and the 48% indium phosphide is lattice matched to the gallium arsenide. Alright, since these two numbers is pretty the same, it's we just for convenience we just say that okay, it's 50%, 50%. It's 50% aluminum indium phosphide and 50% gallium indium phosphide is lattice matched to the gallium arsenide. Then the alloy become between these two alloy. According to bgas law, surely is all lattice matched to the gallium arsenide. So the red material and it has a direct band gap down to 550 nanometer. So the second lattice matched material system is the all-in gap with 50% indium, 50% aluminum and gallium in arbitrary composition range. And it is usually used for red LED with wavelengths ranging from 600 nanometer and to 700 nanometer. Because for wavelengths longer than 700 nanometer, the original gallium outgas is good enough. You don't need to you have a simpler system to do that. So you have a wavelength. If you have a red LED on the road, for example, you see the traffic light is already LED. They are all ALINGAP lattice matched to gallium arsenide. Okay. And the other issue is that because for indium more than 20%, it's even difficult to grow a very thin quantum well in your crystal. So if you want active region with an even longer wavelength, the gas-out-gas in-gas system is also difficult. So what should we do? For example, if we want a nano with a laser or LED in 1.5 micron. Why 1.5 micron? Because 1.5 micron, it has a very low absorption in optical fiber. So it's the wavelength for optical communication. Okay, so if you want to make a light source with 1.5 micron, you might have a indium gallium arsenide with 53%, which is lattice matched to indium phosphide. And the alloy between indium gallium arsenide with indium 53% gallium alloying with IMP is also lattice matched to IMP. So you also have a range of the bandgap design without introducing lattice strength on that. Okay, so INGAS is actually the alloy between INGAS and IMP. And you earned a region of a direct bandgap material on the IMP. And the relation of the XY is around X is equal to around in 9 seconds. X around 0.770 Y. you have so this is homework. You can just try to do a pretty simple calculation. Then you have then you can design your material between 0.88 EV to 1.35 EV. So that's another common system. Okay, so that's the homework.